Yeah, but still, since we have a newcomers from SKMO, so I need to refresh back, or maybe we can introduce a little bit on the design itself. Yeah, so those from SEMO, please bear with me. Yeah, please bear with the rest of your friends from SKMO. Yeah, but I think this is also kind of a refreshment to you guys as well. Yeah, so how we can proceed with the design. Okay, so before we really go into our uh, next project on hull form development, basically. Okay, so please pay attention for those from SKMO. Yeah, I would like to introduce you to actually what is the ship design. Yeah, it's all about. So this is basically a simple exercise. Yeah, to understand. Yeah, design. Yeah, to understand design. So this is actually from SEMO3512, but I think I should at least, yeah, give some introductions lah to you guys so that you can actually understand, yeah, what is actually design. Yeah, and this is the popular phrase, yeah, for design. Yeah, you can only understand design by doing the design. Okay, so now the process of doing design have been started from SEMO 3512, which basically you determine the main dimension. Okay, so but I need to at least share with you so that you can understand that this design course, yes, starting from SEMO 3512 and then you go to 3523, and after this you have 4533. Yeah, integrated design 1, integrated design 2. Yeah, so basically the design course is totally different from other previous courses that you have taken. Yeah, so previous course you are given a problem, yeah, and based on certain equations or certain formulas, so you solve that problems, yeah, based on that one. Okay, but when you look into design, yeah, you are given a problem. Yeah, basically in terms of design process, you are given the owner requirements. Yeah, so last time the owner requirements, yeah, basically this is a continuation. So you are given the ship type, okay, and then you are given the dead weight, okay, and on also the speed. So basically with that ship type, yeah, for example general cargo, you have to make sure that you design a ship which is general cargo, yeah, that can accommodate 30,000 tons, yeah, for group first, and then that ship, yeah, should be operating with a speed of 90 knots. Yeah, so that is how we interpret the owner's requirement. Yeah, so with this owner requirement, ship type, DWT, and speed, so you should come up with a design. So starting from you select or you determine the main dimension. Yeah, then with that main dimension, you come up with the hull form. And from that hull form, you do all this analysis on stability, sea keeping, resistance, and then you also do some in terms of the structures. You also design the structure. So you calculate in terms of the structure strength, yeah, in terms of the weight, and also in terms of the costing, yeah, cost estimation. So these are typically the owner's requirements. So you have ship type, you have DWT, deadweight tonnage, and you also have speed. Okay, so some of it maybe they also provide requirement in terms of class. Yeah, so because the owner they already decided to apply for class. Let's say if they are operating in Japan, so maybe they want to have NK class. Yeah, they want to be certified by Nippon Kanji class. Okay, maybe if more worldwide, maybe ABS, yeah, American Bureau Standard, or maybe we go for Lloyd Register from Germany, or maybe you can go for the NV rule, or if in Malaysia, so sometimes we can also go into SCM, yeah, Ship Classification Malaysia. Okay, so maybe some owner they already decided which class, yeah, that they want to register their ships. Okay, so this class actually you can see if you look at the ship, the body of the ship, you will look some things like you will see something like you know what we call as a load line, um, load line symbol. And with that load line symbols, they have like NK or ABS or LR or DNV. Yeah. So that is determine the class of the ship. Yeah. So they recognize internationally by classification society. Right. So that is additionals lah. Okay. But usually the typical owner requirements is ship type, DWT and speed. So but maybe there are also like a range, yeah, endurance. Okay, because they need to know from um, nautical miles or days they operating it at the seas. So maybe they also give that kind of requirement as well. Okay, so that's how design. So you are given the problems, yeah, you are given the owner requirements, and then that from owner requirement you come up with the solutions. Yeah, basically the solution is more on the design itself lah, the design, the main dimension, the hull form, and then all this analysis, yeah, stability, resistance, and so on. Right? Okay, so that's the approach of design. Okay, so maybe we can go at least maybe let's say one or two, but the rest there's also other exercise that you can go. You can look at SEMO3512 in the link, so to understand more lah um, on the design. Yes, this is more on the simple exercise. Right. So let just me go through problem one and problem two. Yeah. I'm sorry that I'm not sharing this SEMO3512 problems. Okay, but basically the first problem say that a box shape, yeah, you have a rectangular box shape barge. You know, a barge is simply a box shape. Yeah, it's a rectangular, so usually you put um, any cargo, you know, on board of the barge, and then you carry using a towing boat or so on. Okay, so then okay, so problem one, it says that a box shape barge having length, yeah, they have this length of 42-meter, breadth, depth, and so on. Okay, and then it says that assuming the weight of empty barge is 10% of the total weight, yeah, so that to be the maximum amount, yeah, how many tons of iron ore. So now you want to bring on board of the barge is iron ore, yeah, that iron ore is density 5.15 tons per meter cube. Okay, so you need to know how much, yeah, the maximum amount that you can put on board of the barge, yeah, such that the barge is to float not higher than 5.5-meter draft. So that is the requirements. Yeah, so that is the requirement. The barge should float not higher than 5.5-meter draft. Okay, but now you have the size of the barge. Okay, so you are given the size of the barge. But this problem is more like we want to understand how we can proceed with the design process. Okay, so just let me show you how you can solve this problem. Yeah. So for the rest from some more, you can also refresh your understanding on design. Yeah. Let me share this one. All right. Okay. So I'm usually use this books lah. I'm switch between my apa desktop atau laptop with my iPad here. Okay, so the question just now it says that okay, so you have basically a box shape. Yeah. So you have this box shape. Problem one, yeah. Is it lagging? Right. So you have this box shape. Let me know if it's lagging because I'm actually looking at the question just now. So you have this box shape, yeah, and then box shape is having length of 42-meter. Yeah, so this is the 42-meter. Then a breadth of 11-meter. So basically a breadth is if you're looking from front, so this is your breadth. Yeah, so it looks like this. So this should be the breadth. So B is 11-meter. And then you have also depth. Yeah, so this is depth. this is looking from side, yeah, from side. So D is 8 meter. Okay, and then it says that you should bring basically iron ore. So, and then that this barge, yeah, should float not higher than 5.5 meter draft. So basically, if we put something like this, it's a water. So basically, this is yeah, this one is T is equal to 5.5 meter draft. Yeah. So now you need to know how many or maximum amount of iron ore, yeah, to be loaded on the barge. Yeah. So basically, how many? Okay. Then, okay, in design, so basically we start any problem. Yeah, we start any problem with what we call as a design governing equations. Yeah, governing equation. Sorry. Oops. Why is so small this one? Okay, governing equations. Right. So what is this governing equations? Can anyone tell me what is this governing equations? What is the governing equation? Yes, right. Thank you very much. Those who answer. So governing equation is basic equations, yeah, basic equations that you need to hold, yeah, to make sure that you solve the problems. Yeah. So governing equation is weight is equal to displacement. So basically this is a basic equations, yeah, apa tu, Archimedes principles and so on. Yeah. So weight is equal to displacement. It's more like it's not it's equal to displacement. Yeah, displacement, or basically W is equal to displacement lah, means displacement. Okay, and then this mass displacement is basically equal to rho V. Am I correct? Yeah, W. This is a sharp W. Yeah, supposed to be sharp W. Right. So weight is equal to displacement. So in order to solve main dimension problems, yeah, basically you are given the owner requirement just now and so on. So you start with these governing equations, yeah, which is weight is equal to displacement. Okay, so basically if in this problem 1, yeah, you only have a box shape, yeah. So basically, sorry, so this one sikit ni. Okay. So for box shape, yeah, basically a barge. So in our case, it's a barge, right? So basically this volume, okay, so volume is equal to, what is the volume equal to? Okay, maybe anyone from, not from SEMO. Okay, LBT, so L times B times T, right? But basically the volume displacement should be L times B times T times CB, right? So this is in naval architect, so L times B times T times CB, the block coefficients. Yeah, but it's basically volume is L times B times T, right? Okay, but since this is naval architect, so we have that CB, which is actually representing the shape of the hull form. Okay, but in our case, since it's a box shape, so CB is equal to 1.0, right? Okay, so basically, if we rewrite this equation back, yeah, so it will become W is equal to rho times L times B times T times CB, which is 1.0 lah. Okay, and this W is actually, yeah, it's a combinations, or it's consists of W light shape, yeah, WLS plus your DWT, okay, your dead weight tonnage. Okay, so now basically what is in the problem just now, it says that it's a 10%, am I correct? So assuming the wake of empty barge. So when we talk about assuming the wake of empty barge, means that it's a light ship wake lah. Yeah, empty barge meaning that you don't have this machinery, you don't have all the outfitting, you don't have the cargo itself. So basically that is light ship wake. Okay, the empty vessel, yeah, empty vessel. So it says that here in the questions, the weight of empty barge is 10% of the total weight. Okay, so 10% of W lah basically. Yeah, because W here, oops, W is consists of light ship and plus DWT. But of course, this WLS is consists of weight of machinery, weight of outfitting, weight of blah blah and so on, weight of hull, yeah. And DWT is consists of weight of cargo, weight of fuel, weight of fresh water, yeah, weight of provisions, weight of passengers, weight of crews. Yeah, so that is included as DWT. Okay. For that apa tu elements, I'm going to explain more in the next topics basically. Okay. So WLS is not only consists of hull, but basically it consists of machinery and outfitting. You know, whatever that you put on board your vessel, leather. You have this um, superstructures. Yeah, and for wake of machinery, your main engine, your propulsion system, so all that. Yeah, so basically, the light ship wake is basically a empty vessel. Yeah, without any cargo, without any without any fuel, without any food, yeah, without any fresh waters and so on. Yeah, so that is weight of light ship. Okay, so we said that just now, WLS is basically 10% of the total weight, which is W. Okay, so we try to solve this left side first. So basically, from this WLS, so basically you have like a DWT. Okay, or maybe I can put it this way again. Change this color. So W is equal to WLS plus DWT. Okay, this is the left side. So WLS is 10%. So basically, okay, 10% W plus DWT. Okay, so W. Okay, so basically from here, you can rearrange the equation. So DWT is equal to DW. Okay, W minus 10% of W. Okay, or basically 0.9 W. So DWT here. Okay, then this is the left side, yeah. So the right side here, so we know that rho is basically the rho of seawater. So this part, yeah, so this part. So rho is 1.025. So L, just now we have the L is 42 meter. Okay, B is 11 and T is 5.5 meter. Okay, so basically you find this right side, yeah. So right side, so I got 2604.53 meter cube. Okay, so then that is basically left side. Then we go back into the design governing equation. So we know that W is equal to displacement. So basically W is equal to rho V. Okay, so when we write back again these equations, so it should become 0.9 W is equal to 2604.53. Okay, so now we can find this W 2604.53 divided by 0.9. Okay, so what is the answer? So you should find the answers lah. Okay, so how many, what is the answers? Okay, so that is basically W. Okay, and we know that this WT is equal to 0.9 W. Okay, also basically you can also put it this way lah. Okay, if you want to put the equation here, so basically 10% W. Okay, 10% W or the zero, yeah, just like the one just now lah, 0.9 W. So you got this W, 0.9. Okay, then you search for DWT because the question asks you to find the determine the maximum amount tons of iron ore. Yeah, so basically maximum amount tons is basically the WT, which is the weight of cargo. Okay, this one is total weight, so 0.9. So basically the total weight, sorry, the DWT is 0.9 of the total weight. So basically what do you get for DWT? Can anyone try to calculate this one? So that is this one is W, yeah? W is 28393.23. Okay, that is W basically. Am I correct on this one? So this is okay. Oops. Oh, sorry. This one is yes. Okay. So it's coming back to that one lah, to 4.53 tons. Oh. Sorry. Okay. So we cannot solve this. It's coming back to 2604.53. Yeah, but it's supposed to be this is 260.43 is basically the W. Sorry. Okay. This 2604.53, yeah, so this is actually equal to this one, right? So W is equal to 2604.53, okay, which is this one actually. Okay, so 2604.53. So it's equal to 10% of W plus DWT. Okay, so basically we rearrange this one, 2604.53 minus 10% of W, which is again 2604, which is equal to DWT lah. Okay. So basically 2604.53 minus 10% of 2604.53 is equal to DWT. So 0.9 W is also same, supposedly. Yeah, 2604.53, 2344.077. Okay, so all this one lah, 0.9, 2604.53. There are two ways lah, basically. This is the breakdown, yeah. So this is the breakdown of 0.9 W. So you should get 2344.077 or 1 ton. Am I correct? That one? Yes, 0.9 W. Okay, so 2344. So this is the breakdown, yeah. So this is the breakdown. Okay, so this 2604.53 is basically the W. Yeah, and then we know that this W is equal to this rho times V. Yeah, that is the design governing equations. So this is means that it's equal to W lah. Okay, and then that W is consists of this 10% of W, which is because it give you the condition say that 10%, the light ship is 10% of the total weight. Okay, but in the real case, yeah, that one that I put just now, where do you have this ship type, you have the DWT, and you have that speed, yeah, you cannot apply this 10% W. Yeah, this is the condition for this question only, or for this problem. It says that light ship is equal to 10% of total weight. Okay, but in real case, yeah, where you given the owner's requirement, you cannot simply say or assume that light ship is 10% of the total weight. Yeah, there are other approach that you need to apply to get these W elements or weight elements. Okay. Right, so that is the first questions. Then, I share again. Second questions, yeah, to make sure that you really understand the design. Okay, so problem 2 is more like, okay, so problem 1, what you can see from problem 1, so you are given all the parameters. Yeah, you given the length, you are given the breadth, you are given the depth, the T, yeah, these conditions. Then with that problems, yeah, with that existing parameters, so now you only need to find the maximum amount of iron ore. That is the problem 1. Okay, but problem 2, if you look at problem 2, okay, so your design team is requested by a shipbuilding company to design a box-shaped barge. Yeah, so this is basically your ship type. This is a box-shaped barge that enable the barge to store 2344 tons of iron ore. This is the DWT, dead weight tonnage. Yeah, dead weight tonnage is the cargo tonnage lah. Okay, the cargo you bring on board the vessel. So 2344 tons. Determine the appropriate size of the barge, yeah, the length, breadth, depth, and draft. Okay, use the similar correlation or formula as in above problems. Means that use similar correlations means that you can assume the light ship weight is 10% of the total weight. Okay, but you cannot assume this T lah, because you have to design, you have to find the size of the barge. So you are given a problem, you are given the owner's requirement as the problem, and then with that problem, you have to solve it, to determine the appropriate size of the barge. So that is the difference, between problem 1 and problem 2. So problem 1 is actually what you have go through in another courses. You are given the problems, you are given all these parameters and so on, and then with the help of formula, in our case the governing equation, the volume and so on, so then you solve the problems. Okay, but design, you start from not a there's nothing that you can start with. You have length, breadth, depth, and draft. So basically you have 4 unknown. You have 4 unknown parameters. Okay, so if you want to apply back to the equations L time B time T just now, so you have 4 different, or basically 3 lah, L time B time T, right? So 3 different or 3 unknown parameters. So you have to find a way, to find that L, B, T, and in these questions or in this problem, you also need to find the depth. Okay, D. So L, B, D, T. Yeah. You only given the type of shape, you given the dead weight, and that's it. Yeah. So with these 2 owner's requirement, so now you have to come up with the solutions. Okay. So that is the difference between design and other courses like static or dynamic. So this is the difference. Okay, I hope you can see it. Okay, I hope you can see, so that you cannot expect that the design, you simply have this parameter and then you solve based on formulas and so on. Okay, so design is a little bit different. You have the owner's requirement, you translate into the design requirements, yeah, by determining the size, and after this you have to develop the hull form and do all this analysis. So this is design. Okay, right. So now we try to solve problems 2. Yeah. So problem 2 is just actually a reverse back of problem 1. Okay, but let's see you don't have this problem 1, so you do not know the L, B, D, T. Okay, so this is the first problems you are given. Yeah, you have pot shape, 344 tons. So what is the size? Yeah, so that is basically the answers that you need to find out. Okay. So once again, to start, yeah, to solve problem 2, okay, put this way. Okay, problem 2, yeah. Problem 2, so basically now you have this, you have box shape barge. Then you have 2344 tons. This is basically the dead weight, yeah, EWT. Then what else? Okay, you can use the similar correlations, means that your WLS is equal to 10% of W. That's all that you can, these are all the informations that you have. Now you need to find the size, which basically L, B, D, and T. Okay, so this is the problem, the summary of the problems. Right, so now the approach, yeah, the approach is the same. We start with the governing equations. Okay, so in design, we start with these governing equations. Yeah. So W is equal to displacement. Okay, and like I said, the left side, which is the W side, the weak side, WLS plus dWt, right? And the displacement is basically rho times B, yeah, or basically LBT. Okay, so if we want to write further, rho times L times B times T times CB. Okay, CB we can neglect because this is 1.0, yeah, the block coefficient, right? But these equations, yeah, L times B times T, only applicable for boat-shaped barge. Okay, so you have these kinds of barge. Okay, so if you are working on later on, yeah, of course, those from SMO have already worked out that equations. But for ship vessel, ship-shaped vessel, yeah, means that you don't have this kind of boat shapes. Yeah, so you have like a prismatic coefficients for CB less than 1.0. Yeah, it's more like this one. Okay, this kind of shape. So you cannot apply this L times B times T. There's another approach for that. Okay, maybe some of our friends from SMO already can refresh back how we approach that equations. Okay, but for now, since we are working on a box shape barge, okay, we can use L times B times T times CB, yeah, for the volume. But when you are working out your ship shape type later on, you cannot apply this L times B times T. Okay, is that clear? Can I have a response from those coming from SKMO? Because at the moment I only see from SMO. Yeah, so I need to know that those our friend from SKMO already are also clear about this. Yeah, so you cannot apply L times B times T. Even those from SEMO pun sebenarnya ada yang yang still apply L times B times T for ship type. Yeah, so you cannot apply L times B times T for ship. Yeah, so you have learned this actually in naval architecture 1, where you have to apply that Simpson's multiplier 1 or Simpson's multiplier 2, 141, 1332, and you have to get the offset or half breadth data, okay, and then multiply with the Simpson multiplier, then you can get the volume, right? Yeah, so same, yeah, the process is the same. So you cannot apply L times B times T to get the volume of your shape vessel. For box shape, okay, we can use L times B times T. Okay, so coming back to this one, okay, so like I said, WLS, okay, maybe we can have this a little bit. So WLS is weight of hull. Basically, weight of hull here is weight of steel. Yeah, maybe I can put it as weight steel. Yeah, weight steel, and then play plus. Okay, anyone want to add plus what for light ship? WOT. So WOT is for outfitting. Yeah. Maybe I can put it W outfitting or WOT. Okay, what other else? Steel outfitting, and then like I said, weight of machinery. Machinery. So this is W, yeah. Sorry for my writing. And plus what? Okay, weight of machinery. Yes, margin. So you have a margin. So that margin is basically about how many percent? So margin is more like a tolerance, yeah. So because sometimes all the steel outfitting machinery that we calculated is not accurate, yeah. So not accurate. So we have this margin of 6%, yeah, margin of 6%. Okay, that is basically weight of light ship. Now, so when we talk about 10% of W just now, which is the correlations that we can apply. Okay, but in your case later on, when you find the mean dimension, you cannot apply 10% of weight, yeah. So you have to find out the WT steel, you have to find out the W outfitting, you have to find out the W of machinery. Okay, those from SKMO, okay, I will not going into detail on the weight of steel, weight of fitting, weight of machinery. Okay, but you can refer to papan books. Yeah, there are some empirical relations or empirical diagram that you can use to get assumptions of your weight of steel, weight of outfitting, weight of machinery. Okay, or maybe let's say for weight of machinery, another approach that we can use is basically we get basis ships that mostly near to the main dimension of your ship. Yeah, then you get this kind of information on what kind of machine or what kind of main engine that they use on board the vessel. So you can get an information of that main engine, and basically we assume your weight of machinery using a basis ships or a reference ship, a previous ships available in the world, yeah, basically in the Google lah, basically. Okay, so same with the weight of outfitting, there are some empirical relations that you can use, yeah, some formulas, yeah, that you can refer to get the weight of outfitting. Okay, maybe I'm going to share that one later on. Okay, so you need to have this papan book lah. I'm not sure I already shared with you in the e-learning or not, but maybe uh, some of our friends from SEMO can share in the WhatsApp group as well, yeah. Okay, so that is WLS, okay, weight of flagships. And when we talk about DWT, that weight, yeah, it is actually consists of weight of cargo. Okay, so whatever that you bring on board the vessel, in our case here is iron ore, but maybe in your case, yeah, cargo, general cargo, you can bring anything. In case of ro-ro vessel, yeah, there are some groups that designing a ro-ro vessel, Hazim group, I suppose. So your cargo basically is your car or truck, whatsoever that you want to bring on board the vessel. Since it's a ro-ro means a roll on, roll off. Sometimes you also have these passengers. That one is ro-packs. Yeah. So roll-pack is roll on, roll off, means that you have this car or truck, and packs means that you have a passenger. So weight of cargo here is also included the weight of vessel just now. It's not vessel, weight of car or weight of truck or pickup whatsoever lah. Plus weight of passenger. So that is basically the cargo. Okay. In terms of those designing the container ship, so your cargo is basically the container lah. Yeah, your you know, the box of containers. Yeah. What other else? Livestock carrier. So weight of cargo is basically the sheep or the cow. Yeah, whatever livestock that you bring on board the vessel. Tanker is basically on the chemical or whatever liquefied cargo that you bring on board the vessels. A bulk carrier is a cargo in bulk. Yeah, cargo in bulk. So you put in a bulk and then you load it also in a bulk. So that is basically your cargo lah. So cargo in bulk. So DWT is consists of weight of cargo plus, okay, what other else? I already mentioned just now, some more weight. Yes, weight of fresh water, okay, because you need to have a fresh water, not only for drink, but also for shower, yeah, for cooking and so on. Okay, what other else? Fresh water, we put it as WFW, yeah, fresh water. Then W of fuel, of course, yeah, to move your vessel. So you need to have your fuel. Okay, so you need to know what kind of main engine, yeah, because you also have the speed requirement in your real case. You have to have this speed. You have this speed requirement. So you need to find the main engine that should be able to operate with such speed. Yeah, and then with that such speed, you can get the main engine, so you can know lah how many fuel to bring on board the vessel. Okay, weight of crew plus luggage. Yeah, because your crew must be bring their luggage. Yeah, so weight of crew plus luggage here. Okay, and another one is basically weight of provisions. Provisions. Yeah, provision is food. Okay, especially if you sail for a long range, yeah, for many days, so you need to have a lot of provisions on board the vessels. So apa food lah, food, whatever things that you may included as the provisions. Okay, so that is basically GWT. Okay, so now actually the 2, 3, 4, 4 tons that you have, yeah, it actually consists of all this lah. W cargo, WFW, W fresh water, W fuel, and so on. Okay, so that is that 2, 3, 4, 4 tons of iron ore only consists of this W cargo, right? But basically the WT should consist fresh water, fuel, fuel, cruise, and so on. Okay, so now, yeah, back to this how we can solve this problem. So once again, yes, ballast. Better put this one, W ballast. Okay, but W ballast maybe sometimes we don't need the ballast, but sometimes we need to have the ballast. So according to the operating condition of the ship. Okay. Thank you. Go. I'm gonna put it on as well. Okay, so this is the. Okay, sometimes maybe you will use this kind of terms. Yeah, this is W payload. Okay, and the rest is more like a variable operational cost. Yeah. So this is more like operational cost. So variable load, or the variable weight. This one is load weight. Yeah. So which means that the load that you are paid for. Yeah, you get money from this load. So that cargo lah. Okay. So coming back from this one, so we have this governing equation. W is equal to displacement. Okay. So WLS plus DWT is equal to both times just now. Okay, so WLS, we know that is 0.1 W. Okay, but once again, in your case, you cannot apply this as 0.1 W. And DWD, we have 2344. Okay, rho is basically 11025. Okay, so we have this L times B times E times CB, which is 1.0. Okay, so on 0.1%, basically we can for this left part we can solve it. Yeah, so W is equal to 0.1 W plus 2344. Okay, so W 0.9 W is equal to 32344. Right? So you can get this W is equal to it's now 260.53. Right? 260.444. 260.444. Okay, so that is the left part. The left part. Yeah. So basically we rewrite this again because you already get the W part. Yeah. So when you write this one again, so 2604 2604.453 is equal to 1.025 times L times B times B. Okay, so 1.025, okay, you can solve that one. 264.53 divided by 1.025. So you got 2541. Yeah, L times B times B. Right. So this is where the design fields comes. Yeah. So you have three unknowns here. You do not know the L. You do not know the B. You do not know the T. But you have this left side to help you with it. Yeah, you have this weak element to help you. Okay. Only that the right element, the displacement L times B times T, so you can help. Okay. So how are we going to do this? Any ideas how we're going to do this? Ratio. Thank you very much, Zainal. Thank you, Hazim. Shafi'i, trial and error is basically the what we call as the process, trial and error. Okay. So okay, yeah, especially those SKMO. So this is how we deal with this design. So we don't have these three unknown, yeah, LPTT. Okay, so the approach is basically this is the design approach. Okay, we use a ratio. Okay, a ratio, and this ratio is based on literature review or literature study. Yeah, means that you go to Google, you read any paper, yeah, or you read books, okay, or you can also get this ratio based on common practice in the industry. Okay, so maybe in the industry, let's say one ratio, okay, there are actually three ratio, yeah, but there's also more ratio that you can use, but this three ratio is the is a significant or enough to get you the LBT and D, of course. Okay, so the first ratio that you need to know is L upon B ratio. Yeah, LB ratio, L upon B ratio. Okay, so common practice. So ratio here you can get from literature, from journal, from books. Yeah, journal, books. There are some papers. This is this is the part where you don't actually like. Yeah, those from SEMO last time. So you don't actually like that part. So there are reliable journal articles, yeah, that you can refer. They do a lot of study and then they come up with this empirical diagram which consists of a lot of L upon B ratio that you can refer. for many types of vessel. Yeah, for barge, for cargo vessel, there are different L upon B ratio. For tankers, there are different L upon B ratios. Okay, so there are many ratios that you can refer to. So that one is from journals or from books. So from books, basically from Papan books or from Watson books. These two are the most, I would say, comprehensive books lah that you can refer. Or you can also base on a common practice. Common practice. Common practice ni means that you go into industry, you say that how many L upon B ratio that you use to calculate this main dimension. Yeah, so that is a common practice. So L upon B means that length per breadth ratio. For barge, yeah, it's typically about 3 to 6. Okay, 3, 4, 5, 6, 3.1, 3.2, 3.3, 3.4, whatever lah. Yeah, within that range, 3 to 6. Later, I will show you, you can also find this L upon B ratio in Papan and Watson book. Okay. More than 6, usually for long ship. Yeah. So from this L upon B ratio that you refer to literature or from common practice, yeah, so you have to decide, maybe let's say you want to decide L upon B 5 for the start. Yeah, for the start you want to choose L upon B 5. Maybe you say that I want to go for maximums lah. Maybe you can start with L upon B 6. Okay, so there's no wrong or right. Yeah, let's say you want to take 4, 5 okay, 5 okay, 3 pun okay, or 3.5, 3.7, whatever. Okay, as long as it's within the range. Okay, that is how you select for the ratio. Then the second ratio that you need to have is B upon D ratio. B upon D. I hope you can see this D. B upon D. Okay, and from common practice or from books, B upon D for barge is usually 1.0 to 1.5, I suppose. Okay, breadth to depth ratio. Okay, this is a common practice. Yeah, breadth to depth ratio. The breadth to the depth ratio of the barge usually 1.0 to 1.5. So once again, you select. Yeah, you select any value. B upon D, maybe I want to take 1.5 or maybe I want to take 1.0. Yeah, doesn't matter as long as within the range. That is the second ratio. And then the third ratio that you need to know is T upon D. Yeah, the draft to the depth ratio. Okay, so usually this one for barge, it's typically 0.8 lah. Typically, but for other shape of vessels, you need to refer to other books or literature review. Okay, so now back to these equations that we have here. So L times B times T is equal to 2541 tons. Yeah. Okay, so we can actually do this mathematically. Yeah, you have this L upon B times B upon D times T upon D is equal to 2541. Then you can rearrange back all together. Yeah, but that's what mathematicians do, but not naval architect. So we don't solve this mathematically. Yeah, unless if you want to go to mathematics, so by all means you can solve this kind of equation as well. We have one method. We call this what is the method? What is the method that we solve this mathematically? Those from SEMO. What is the method? We have three methods of determining the L. We have this estimate L. We have the calculated L. Is it approximations or what? That you solve this mathematically. Iterative. That you change this one. Is a calculated L, right? So calculated L where you solve this mathematically. So okay, that is another things, yeah. So you can solve this mathematically yeah, mathematics, all that apa differential, it's not differential equations lah. Just you change this and you substitute back and so on. Okay, but we naval architects, we don't do this. Okay, what we do is basically, I think Shafi'i answer just now is a trial and error. Okay, or iteration process. Trial and error. Trial and error or iterations. It's not or, it's and, yeah, an iteration process. Okay, trial and error and iteration process. Okay, so now you have all this ratio. L upon B you select 6, B upon D you select 1.5, and T upon D you select 0.8. Okay, so basically we start with what we call as a trial L. Okay, okay, because it says that trial and error and iteration process. Okay, iterations means that you do it several times, yeah, until you get the most optimum or the most appropriate size. Okay, so let's say, yeah, with a first trial, okay, maybe I want to start with L is equal to 30 meter. Okay, right? So it just any value. You can start with L100, you can start with L50 meter. Okay, but what I suggest last time is, okay, can anyone answer me? Those are from SMO. What I suggest you to do, to start with the L just now, back then. There are some values that you can start with. Anyone from SMO? Okay, otherwise you start from random value. You can start from L 10 meter. You can start L from 20, 30, 40, 50, or you can start L from 1000 meter. It's up to you. Okay. Yes. Thank you, Go. Thank you, Daniel. So what I proposed uh, to them last time is basically you try to get a similar DWT shapes. Yeah? There's a lot of database out there on shape in the world. Yeah, so you just key in the type of shape, just key in the DWT of the ship. Okay, maybe the type of ship is general cargo, for example. Then the DWT just now is 30,000 that weight. Okay, so you key in that value and see what are the vessel available in the world. And you get the LBDT of that similar shape. Okay, or reference shape or basis shape we call it. Okay, so get that similar DWT from literature review or from Google. Yeah, basically. Or from books, yeah, whatever that you can find. Okay, so maybe for this type of vessel, okay, for barge just now, okay, I try to find that 2, 3, 4, 4 ton, and maybe it's around 30 to 50 meter length. So I start with 30 meter. Okay, so I start with 30 meter. So now you have the L upon B just now is 6, B upon D is 1.5. Okay, I put it here, yeah. T upon D 0.8. Okay, so when you have this L 30 meter, and then you know that your L upon B is 6. So L upon B is 6. Okay, your L is 30. So B is equal to 6, right? So you can get your what? Your B. So which is 30 divided by 6. So what is the value? 30 divided by 6. So B is your, Masya Allah. Ini pun nak pakai calculator. Oh, 5. Thank you very much. Right, so that is B. So now you get the B. Then you have your B upon D is equal to 1.5. So you have this B that you have calculated based on L upon B ratio just now. So B upon D, B is 5, D 1.5. So you can get your D, 5 divided by 1.5. Okay, it should be 3.3 meter. Am I correct? Yes, right, 3.33. 3.33. And then, so basically you have your B, you have your D. With this assume L or trial L. Okay, this is only the first trial. So T upon D is equal to 0.8. So T divided by your D is 3.33 is equal to 0.8. So you have your T, which is 0.8 times 33. So 2.67. Okay, then what should you do? Is this the correct LBDT? So now you have all together, yeah? So you have already determined your L, you have your B, you have your D, and then you have your T. That's it. So okay tak? Can proceed. So is this the good size, or is this correct? I wouldn't say correct lah. Is this the appropriate size to carry that 2344 iron ore? Right? So you need to check. Yeah. So you need to check again. Key in back into this governing equation just now. Okay. So you key in back into these governing equations. Okay. So L time B time T equal to 2541. Yeah. So this governing equation. So I write back these governing equations. L time B time T equal to 2541 meter cube, yeah, units. Okay, so you have your L tadi just now is 30. So 30 time breadth is 5 and then your depth is 2.67. Okay, right? Okay, so do you get this value of 2541 or not? What is the value? Okay, betul ke tu Hazim? Part je. Betul ke tu? 400.5. Right? Okay. Ya. Yang lain macam mana? Anas, Amir Irsyad, siapa lagi nama saya nampak kat sini? Atira. Who else from Ammar? Ammar pun ya, from SCAMO kan? Hafizi. Who else? Who else from, I think it's about 8% at 8 of you. Okay. So yes, basically 405. Yeah, so this part is 400.5. So basically it's not the same as 2541. Yeah, it's not same as 2541. You need to get this 2541 because we know that W, sorry, this one is not W. This part is displacement, right? Rho V, but rho we already calculated. Okay, rho V is equal to W. So now this governing equation is not satisfied. So you have to try with another value. So that's why we call it iteration process or iterative process. You change now the value. So last time, what your friend from SMO did, so they have this lot of Excel punya a long Excel. So they start from 30. Yeah, you remain the L upon B first. L upon B, B upon D, T upon D. Tadi berapa? 6, 1.5, 0.8. Then they get this L, B, D. Then they find this error. Yeah, I do not know what value of this error. So the error basically, how do you get the error? You divide with the displacement lah. Weight minus displacement and you get divide by displacement. You get the error, right? It's like the error of experiment. Okay. What is the error here? Can someone calculate the error? So displacement W or W displacement, right? Time 100%. Or you can just actually apa tu? In terms of percentage, or you can also here is just displacement, sorry, W minus displacement. The displacement here. So 405 minus 2541. So you get some error here. But basically error is in terms of percentage, yeah? So you divide by displacement again. Right? So you get in terms of percentage. So now, okay, so you found that it's too small. So you need to change. So you need to change. You try with 35. Then or maybe you try with 40. This is first trial. This is second. This is third. Then you go again until you get this error is equal to zero, almost zero. Meaning to say the left side and the right side is equal, 2541 or 254. Maybe this one is 2541, maybe this is 254.9, maybe whatever lah. But it's almost zero. Yeah, the error is almost zero. But you maintain the LBDT ratio first. Okay. But whatever value that you get here, maybe apa tu, the question just now is berapa? 42. Am I correct? So whatever value you start with 42 ni, so you get 42, you get 11, you get 8, you get 5.5, let's say, right? Okay, then you get the error is zero. Okay, but this dimension, LBD that you get, this is not, even though it is correct, which give you a zero error, almost zero error, we sometimes this is not an optimum size. Yeah, optimum size means that not only based on the dimension, not only based on the displacement or the owner requirement, but they also must be considered the financial, the cost of the apa tu, the production costing. Okay, so when you do that, so then you have to calculate the cost. Yeah, there are some way to calculate the cost. Okay, then you found out that the cost is a bit high. Yeah, so there are the what we call as, anyone remember how do we optimize last time on choosing the best design? Do you remember on that one? Now, optimizations and so on. Where you actually you get this LBD, then you get this, yes, surface area. Basically, that surface area will get you to the number of plate. The surface area of the plate will get you into the costing. Yeah, we assume the size. We assumes for one plate. Okay, what is the cost? Okay, and then with the total surface area of the vessel, or of the dimension that you get the cost. Okay, so when you get the cost, you will see that the cost may be higher. Okay, then we change the ratio. Okay, maybe, okay, you say that maybe when you have this cost plate, is about the cost, the surface area of the plate will give you a numbers of plate with a higher surface area. Okay, so then you say that, of course, a bigger surface area of plate means that a bigger cost, right? Because you need a lot of sizing. You need a lot of plate. Okay, so bigger numbers of bigger surface area of plate, which means that bigger cost of productions of the vessels lah, basically. Okay, so we do not want to have a big cost. It means that we need to have an optimum surface area of plate. Okay, so then what you do is basically we change the ratio. We want to see, okay, we want to see what happen if we change the ratio. Okay, let's see, we fix ratio B upon D and T upon D, 1.5 and 0.8, but we change L upon B into, just now I take maximum is 6, right? Then I change to 3. Okay, basically this is the first iteration, yeah, the first trial and error process. Okay, but now I change the L upon B equal to 3, but I fix the B upon D 1.5 and T upon D 0.8. Then you do again the trial process. Okay, so first trial you start maybe with the last value that you get, 42 L. Then you get what is the B, what is the D, what is the T. Then you find the surface area, the total surface area of plate. Yeah, I know some from SMO pun miss this part actually. I'm not sure whether you miss or you don't attend class or you don't remember. Okay, you get the surface area of plate. Okay, basically if you have this kind of barge, yeah, this is barge. Okay, but of course this is not applicable for ship, yeah. ship vessel, because you have to do a scaling drawing to get the total number of plate. Yeah, but you find the surface area of plate, yeah, or size of the plate. Okay? So basically this is L, this is D, and this is B, right? Okay, so you can get this total surface area. So surface area, total surface area, surface area. So you have, kalau you tengok this way, it's like this actually kan. Okay, so you have okay, this plate, yeah, L time D, right? And you have two part of it actually. You have two plate of this, yeah. So basically this is L time D time 2. Or maybe I can put it 2 L time D, right? And plus another area here, this part, yeah, this part and this part, okay. Basically D times B, am I correct? So 2B times D, okay. Plus you still have this on top of the vessel. Okay, this is the, oops, sorry, salah. Top, yeah, this is top plate and the bottom plate here. I hope you can imagine this, right? So you have 2L times B. Okay, so basically you find lah the total surface area. Maybe we can put this A. Okay, so then what you do, tadi you change this L upon B. Maybe after this you change another L upon B, you take a middle one. So now, just now we say that the ratio is 3 to 6. So maybe you take berapa? Maybe 4 or maybe 5, up to you lah. Or maybe you want to take the middle. So 4.5, it's up to you. It doesn't matter. So now, so basically what we do is that we have this kind of table. Okay, so first trial where you have L upon B is equal to berapa tadi we start? 6. Yeah. Then you have L upon B 3. You have L upon B 4.5. Yeah. Okay, so you put the L, you put the B, whatever that you get yang almost 0 tadi. So LBD and this surface area. Okay, so this surface area is coming from this formula. Okay, when you have this table, then you can plot a graph. Yeah, so L upon B, or maybe you can also put a length. Yeah, L upon B or L, doesn't matter, whichever. And this is area, the surface area. So we say just now, bigger surface area mean big cost. Okay, maybe you will have some graph like this. Okay, so bigger L upon B, bigger A. So maybe we can take a middle one as our optimized size. Okay, or maybe usually you will get something like this. Okay, a U-shaped graph. Okay, so this is basically the lowest point here is what we call as the optimum point. Okay, so this optimum point is basically the what we call as optimum size lah. Optimum size for whatever vessel that you are working on. Okay, so in our case, the optimum size here is for the barge, maybe 42 meter. I'm not sure lah. Okay, maybe 42 meters. So you have to do this iteration process, trial and error process. You change the L upon B ratio. Okay, it's actually a long process. It's not you just change L upon B. So once you have find the correct L upon B or the optimum L upon D, then you change the B upon D ratio to see which B upon D will give you a more optimum size. So that is an iterative process. So it's a long into this process actually. Yeah, but most of your friend from SEMO last time, main dimension, I think is, I asked them to not go too detail lah. Yeah, as long as you do some iteration process and you change one or two area ratio, L upon B ratio, and then should be enough. Okay, so that's how we solve as a ship designer or as a naval architect. That's how we solve a design process. Okay, is that okay? Especially for those coming SKMO. So that's how the process of mean dimension determination. Yeah, that's what all your friend from SMO did last time. Yeah, they go through quite numbers of weeks. I think it's about 4 to 5 weeks to finally settle down with their mean dimension. Okay, and that this L upon B ni you need to make sure sampai dapat error zero lah. At least zero, almost zero. Okay, and when we said about apa L tadi ni, there are three actually methods to get this first L. And first is trial L, where you actually just take any L, and then we also have this estimated L, yeah, estimated L, and then we have a calculated L. So calculated L where you actually solve mathematically, then you get this calculated L. So you get directly the L, the correct L for the vessel. So you don't have to do any trial. Okay, that is calculated L. Estimated L, how we do that for estimated L? For estimated L, anyone? How we do the process for estimated L? This is for L. Method to get L. To get L, is it to start with the L lah basically, yeah. So the first is trial L. Okay, you select any L. Second is calculated L. Okay, of course I'm not going into detail this one, yeah. I am so sorry for those coming from SKMO, but you can always refer to my literature from SCMO. So calculated L, so you have all this apa tadi L time B time T 2544, yeah. And then you change this L upon B, B upon D times T upon D, yeah, 2544. And then maybe you assume, so oops. Okay, we assume this is mathematics lah. L upon B is equal to alpha. Okay, B upon D is equal to beta, and so on. And then we solve it. Okay, so you can search that one in my previous lecture. Then we have estimated L. So yes, I think someone give me an answer just now. So estimated L is that we estimate the L, which is L is equal to displacement to the power 1/3 of the displacement. Okay? We estimate the L is equal to 1/3 of the displacement. Okay, so you have displacement, you know your displacement, then 1/3 of this displacement, that is your L basically. Okay, but still you have to calculate the error. Yeah, you have to calculate for the error to make sure that whatever value that you get here give you almost or equal to 0. So that's how we go about mean dimension. Yeah. If I want to summarize, last time one of the questions from test is that the flowchart, the flowcharts of the the flowchart of determine the mean dimension. Okay, so you have to know this flowchart. So we start with design governing equations. Okay, basically, if I want to expand this equation, so WLS plus dWT is equal to rho times L times B times T times CB. It's actually another thing, 1 plus S. Now 1 plus S is basically for the plating thickness. Okay, but sometimes we can neglect this one lah, 1 plus S. There are some guideline for this S, which is 0.05%. Yeah, so it's equal to 1 plus 0.005 or something like that. But you can neglect that one. But for verifications, we can include this. Okay. So this is the first step. You have this design kind of equations. This is the expanded equation. Okay. Then the second step is basically you select L. Right? So select L. This is a trial L. This is a trial L first. So select L, or you can also use estimated L, or you can use calculated L. Okay. So select L. Or basically you choose, then you choose all the ratio. You choose L upon B, B upon D, T upon D ratio. So T upon D ratio. Right? Then you work out the displacement. Okay, so you find the W is equal to displacement. Okay, so if yes, then you can get the LVDT. Okay, if no, if this is no, means your error is more than 0. Yeah, so then you have to go back into this select L. So this is the iteration process. Okay, so that's how you do iteration process to determine the mean dimensions. So what your friend did last time for SEMO3523 is the same process. Okay, they start with the weight dimension. They start with the owner requirement. Okay, then they come up with the L. They do the iteration process and so on. Then they get these mean dimensions. Okay, but additional to that, because here this is for box shape, yeah. So how you can get this, because you only know this part, DWT. So how you can get this value? How are you going to know the required displacement? Anyone? How are you going to know the required displacement for this one? So if you're coming back to your owner's requirement, yeah, so you actually start from owner requirement before you start with the government equation. Okay, so this is not part of the problem anymore. This is the real process of determining the mean dimension. So you start with the owner requirement. Okay, you start with the owner requirement. So you have this ship type, you have this DWT, and you have the speed. Okay, so from that owner requirements, yeah, so you have DWT. So this is given to you. But some of you have TEU, yeah, 20 equivalent foot. This one is for container vessel. So you are given in terms of TEU, 20 equivalent unit, yeah, 20 equivalent foot unit. That one is for container. Okay, you are given in terms of TEU. Okay, later I'll show you again, yeah, for from SKMO. So some of it, yeah, container ship we have in terms of TEU, yeah. So 20 equivalent. So you need to find a size of vessels that can fit that TEU. Okay, and some also are given in terms of what else? I think it's only DWT and a passenger. Yeah, for RoPax ships, the requirement is given in terms of passenger. For RoRo ships, they are given in terms of GRT, gross tonnage. So TEU, or number of passenger, or gross tonnage, GRT, gross tonnage, yeah, and DWT. So there are four owners requirement, four different owner requirement. Depends on type of ship. yeah, TEU, number of passenger for ROPEX, GRT for Ro-Ro vessel, and DWT is basically for what we call as weight-based design. Okay, so there are two design base. Yeah, first one is a weight base, weight base, weight based design or weight based ship basically. Yeah, weight base. Then the second one is a volume base. Okay, weight base and volume base. So for weight base, directly DWT you are given, so then this is DWT lah. Okay, or you can also get this value based on DWT over displacement ratio. Okay, so you have this DWT, so you can get your displacement ratio. Okay, so you have DWT over displacement, maybe some of it maybe 6, I'm not sure, this depend on type of ship. Yeah, so with this DWT you can get the displacement required. Okay, so with this displacement required, so you can work out your LBT, yeah, get the displacement. So if yes, then you can get the LBT. If no, then you should select another L. Okay, that's how we do for weight base. Yeah, for volume base, TEU, number of passenger, GRT, they need to convert that TEU value, number of passengers, and GRT to DWT before they can proceed with the main dimensions. Okay, is that clear for SKMO students? Yeah, they are weight based and also volume based design. So weight based usually itulah yang ship carrying heavy cargo, yeah, tanker, bulk carrier, cargo, general cargos, yeah. But volume base is based on volume. Yeah, the container, the passenger ship, the ro-ro, ro-pax vehicle. So the volume is more important than the weight. You need to make sure that number of vessels or number of passenger, yeah, that you want to bring on board, yeah, with the main dimensions that you calculate or that you determine, it can accommodate such numbers of passenger or such number of car or truck or whatever that you bring on board the vessel, or such numbers of TEU required. Okay, so then only you can proceed with the selection of main dimension. Okay, right, any question? No questions? Okay, so for those from SKMO, like I said last week, so myself and Dr. Xiao, we agreed to give you extra assignments lah, yeah, to make sure that you understand, you know, the part of main dimensions. Otherwise, you have skipped that part, which is actually important because last time from SKMO curriculum, you have to actually determine the main dimension as well. Okay, so that part is missing here in SMO3523 because you are not taking SEMO3512. So we need to have that extra assignment so that in your achievement of what they call course learning outcome or program learning outcome, there are some evidence that you have you did some tasks on the main dimension part. Okay, so I'll share in the maybe in the e-learning lah, or maybe in WhatsApp, the extra assignment for those from SKMO only. Yeah, for SKMO you don't have to do anything for main dimension, but I need you to relook at your report, yeah, because some group missing the weight verification part. Yeah, weight verification part is missing. Yeah, like I said, the DWT given to you is only the weight of cargo. So you have to look into the weight of fresh water, weight of fuel, and so on. Yeah. So to make sure that the main dimension that you get is the correct one lah, basically. Okay, is that clear, yeah? For SKMO, SEMO and SKMO. Right. Okay. So here I just like to recap back on this one. No, 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 you don't have to submit. Yeah, but you have to relook again the weight verification part. If you do not have that weight verification part, you need to relook. Yeah, and then because the assessment part already done. So if you submit to me the weight verification point, there's nothing that I can do to change the marks previously. But you have to make sure that the main dimensions that you're going forward, because after this you're going to develop the hull form, so you need to make sure that hull form is basically based on the correct main dimension. Yeah, so you need to relook again back to that part. Yeah, okay. So this is the apa ya, this is actually the step to determine the main dimension last time. So you look here, week 3 to 7. So basically, they spend about 4 to 5 weeks, yeah, to come up with the main dimension. So for those from SKMO, you have to go through your group project. Yeah, you already know your group. So all the group project report already in the e-learning. So please get your respective design report, group design report. Go through that design report, yeah, and I'll give you the extra assignment that you have to do lah. You have to submit. Okay, so I hope from the lecture part just now, yeah, the refreshment or the recap of the main dimensions and your group design report, it can help you to understand better on how we do the main dimension. Okay, this is the Papan book. I'm not sure whether you have it or not yet. Okay, but you can see this. Okay, I also cannot remember. Maybe here. Let me others questions. Okay, because last time, okay, oh, right, okay, okay, maybe to answer Go punya question, okay, but before that, because I just opened this Papan book just to let those from SKMO know how we can use these books, yeah. Um, okay. Yeah, go. I also do not. I cannot remember which part is. I think it's the chapter 2. Yeah, there are selection of mean dimension and calculations. Okay, so basically this is some reference. Typically, this is the reference that your friend from SEMO used last time. So there are DWT over displacement ratio here. Okay, so you have the DWT, okay, given to you, or if it is not given to you, and you are given in terms of TEU, numbers of passengers, and GRT. Okay, there are some empirical diagram. Okay, in Papan book as well, there is a Papan book empirical diagram. In appendix here, appendix here, I cannot remember which appendix. But let's see. Those for containers last time, do you use Papan book ke, or do you use apa? Saya pun tak ingat. But I think Roro ada dekat sini. There's a lot of this empirical diagram, yeah. Okay, let's see this one, yeah. I'm not sure what is this. This one is for chemical carriers. Chemical, usually I give DWT. This one is general cargo. Let me see in terms of Ro-Ro, yeah. So this one is Ro-Ro passenger, basically ROV packs lah. So this one, yeah. Is there any on this one? I also cannot remember this one. I think last time Azim benda dekat mana? Refer paper lain Ro. Okay, this one ya. Paper lain dan ada dari papan. Okay, so contoh this one lah. So let's say Hazim group is on Roro. So they are working on, let's say Ropex, sorry. That one is Ropex, right? For those, this one is Roro, This one is Roro, I think. This one is Roro, So Roro vessels, let's say group number 5. So you are given 40 GRT, 40,000 GRT. So from here, 40,000 GRT. So these are based on a lot of data available, from ship, that they come up with this regression analysis. Okay, for container they use empirical, but from internet papers. We don't call it internet papers. We call it journal papers or articles. Okay, journal articles. So like I said lah, so you can use from any reliable papers out there, or you can use books. So depend, yeah. So for example, this one for Roro, this one from Kalukairi Nos paper is actually from paper as well. Okay, but they put in this book, yeah. So this one, so you have 40,000 GRT, then you convert to DWT, so it's about 20,000 deadweight tonnage. Yeah, so from that deadweight tonnage, so you can get the displacement. From that displacement, you can get your LBDT lah, basically. Okay, so this is some regressions diagram, some empirical. There are some also empirical diagram or some empirical relationship that you can use to convert that TEU or GRT or numbers of passenger. Also some here. Okay. This is DWT upon displacement ratio. For L upon B, B upon D, cannot remember which page. Last time I asked them to put the page numbers. Then I also cannot remember which one. Okay, but that is Papan book. Another book that you can refer to is Watson book. Watson book is more, I can, the Papan book, this one, the ship design methodology is more comprehensive book lah. Watson book is already too old. Yeah. Sorry, I think this one good. What page I also cannot remember what page. L upon B, B upon D. Yeah, this one, yeah. This one. Okay. So we have this L upon B, B upon D, L upon D, T upon D ratio. But this one is more containers, bulk carriers, tanker, yeah. But in Papan book, there are one table on L upon B, but I cannot remember which page. Okay, but you have to go through lah. There are one table on L upon B, B upon D, T upon D ratio that you can refer to. Or like your friend said just now, you can refer to other paper as well. Okay, for particular type of ship. So that's how we do the searching part, yeah, that most of you are actually a bit down with that one because you cannot find the correct or the good or reliable resources. Okay, so that is for how you do the main dimension. Okay, but just to answer Sir Go question just now. Okay. Okay, wait, give me a second. Okay. Okay, so this is a continuation, yeah? Right. So last time, so once your friends, they get the mean dimensions, yeah, and they calculate the error, okay, then one of another important point or another important step, yeah, to make sure that your main dimension is correct is they draw initial GA and they do initial capacity verifications, yeah, initial GA drawing. Okay, I hope after this maybe you can have a quick discussions with a new member and to see your initial GA drawing and capacity verification or capacity calculations or capacity check, whatever the lot of terms that we use. Okay. So last time with the main dimensions that you get from the main dimension part, then with that main dimensions, I asked to do initial GA drawing. Okay. So your friend have come out with the initial GA drawings. Yeah, you can look in the design report. So uh, and based on some rules and some guidelines on the initial GA, so your friend have come out with maybe this is like this one, yeah. So this is a bulkhead, and maybe you have several bulkhead, yeah, depending on what type of vessels. Maybe you have a double bottom here. Okay, so this is basically a cargo area. So this is another bulkhead. So this is your main engine room, ME room. This is your propulsions. Here maybe you will have a superstructures. Okay, I'm not sure. That one is also depend on a basic ships or reference ships. Yeah, maybe there are 3 layers or maybe there are 2 levels of superstructure. Is up to you. Okay, if you have too many crew member, yeah, so basically you may have more than 1 or 2 superstructure, and this is your wheelhouse, then this is the accommodation part and all the cleaning and so on. Okay. So that is the initial drawing, and based on that initial drawing, yeah, so we do a capacity calculations, yeah, where you check with the main dimensions. So that the GA drawing have this profile and also the half right view, yeah, plan view. So you have this cargo areas, yeah. Okay, this is the cargo area. Maybe here you have a tank, freshwater tank or ballast tank. This is where you put the fuel tank and so on. Okay, whatever lah, depend on your GA. Okay, with that GA, then we do a capacity check or capacity calculations. Yeah, especially for the cargo area. Yeah, so you have this area. Change this one. So it's just an initial capacity. So you have this, maybe this is L, this is B. Okay, this is L, this is B. Okay, this is what you done last time. So with that LB, then we search or you assume, you calculate for whether the volume, if you have the volume, yeah, you can multiply with the density, then you can get the weight. Yeah. So with that initial GA, we calculate for the capacity check or capacity verifications. Yeah. Whether it can accommodate the owner requirement given to you or not. Yeah. Kalau DWT lah. Kalau TEU, in terms of TEU. So TEU, they have all the container on board the vessel, on board the deck cargo, the main deck. Okay, and some of it may be here. Yeah. Dia ada dekat dalam, dia ada dekat luar. But this must be according to TEU size lah. Yeah. So those for TEU, they found out the TEU size, the size of the container tu. Okay. Then they put on board the vessel. Yeah. So maybe it's about 40,000 ke? Go. What is the value? 40,000. 4,000. 10,000. 6,000. Okay. 3,500 and 6,000. Okay, for container ship last time. So it need to have 3,500 of this container on board the vessel. Okay, so when a Go do that last time, so then with that mean dimension that they found out at the mean dimension part, yeah, it need extra. Am I correct? Extra. Either are you changing the length or are you changing the breadth last time? Cannot remember. I think you are changing the breadth. Am I correct? Yes. Yeah. Okay. They are changing the breadth. So maybe I'm not sure. The breadth last time maybe 10 meter. But then when they try to accommodate that TEU, yeah, with the initial GA, they cannot get 3,500 TEU on board the vessel with this breadth or with that length or with that dimension. Yeah. So then you have to alter a bit the equation, the size. So maybe like Go did last time, is actually they expand the breadth. So it's a lot bigger lah than whatever value that they get here. So B is 10 meter, maybe now B is 15 meter. Okay, then they can accommodate 3,500. Okay, so that is capacity calculations. So not that you only stop until the main dimension. So then you have to do the initial GA drawing, then do the capacity calculation. So that also will be done this semester. Yeah, once you develop your hull form, yeah, you come out with a comprehensive GA drawing. Last time it's just initial GA. You don't have this all details on. You just have a preliminary GA drawing. So now with your hull form, with your hull lines plan, you come out with the GA, and then with that GA, you recalculate the capacity calculations. Yeah, because last time you just based on the main dimensions and then you draw the initial GA. Okay, but now you have developed the hull form. Okay, maybe the shape is a little bit different, the size may be a little bit different, and so on. Okay, so now you have to recalculate the capacity calculation, the correct capacity calculations. Okay, so but to answer Go question just now on whether you need to recalculate the weight part, no, you don't have to. Okay, you don't have to recalculate the weight part lah. Okay, because you're going to recalculate the weight part in the weight estimation later on. So now with the hull form that you have the hull form that you have developed, yeah, with the initial with the initial GA block, with the GA drawing, that soon you will put a detailed GA drawing. Yeah, basically maybe the size, the correct size of the accommodations, yeah, the correct locations of the bulkhead, yeah, and so on, yeah, numbers of crane that on board the ships and so on. Okay, then in the weight estimation later on, you're going to recalculate. Okay, so you don't have to recalculate with the latest dimension. Okay, because now with all the calculations and all the estimation that you have done, okay, but because when you do the main dimension part too, maybe the ratio is not the correct ratio lah, basically. It's still not an optimum ratio that you use to calculate the main dimensions. So now only when you do the GA, you do the capacity check, you see that it's not accommodate the TEU numbers, or it cannot get the DWT given to you, then you have to change the size and so on. So it's okay. Means that the process of main dimension is not um, it's not it's not done until you get the most optimum size lah. Yeah. If you read in the upper articles and so on, there are the optimization process, yeah, that you do using a programming and so on until you get the most optimum main dimension, which you cannot do in Excel or manual calculation. So you have to have a program and so on, coding and so on for that one. Okay, otherwise it will be a lot of work to do. Okay, so that's about it for main dimension. Any questions? So sama ya. So for cargo vessel, Roro vessel, sorry, Roro vessel last time. What Hazim did, Hazim Group did. So basically, they put they know the size of vessel. It's not vessel. The type of apa Roro, the type of car or type of apa last time, pickup ke apa ke. Then they know what type of it. They know the dimension, the size of the car. Then they put in the initial GA to see whether they can accommodate such number or not. Okay, same with those with row packs. Yeah, 1,000 passengers. So they have this cabin, they have this sitting area and so on. Then they look and they estimate or they do capacity calculation to see whether with that size, with the numbers of vessel, number of deck, yeah, whether they can uh, accommodate such number that given by the owner, yeah, on the owner requirement. Yes, yes. So basically, you still can change the dimension in IDP1. Maybe especially when you develop the hull form later on, yeah. When you develop the hull form later on, maybe you have to extend some of it because apa tu, the bulbous bow pun you have to extend a little bit and so on. Yeah, so something like that. Yeah, so you still have maybe you can change or maybe you don't have to change. Yeah, if it's up to you. Yeah, as long as the owner requirement is satisfied, means that you fulfill lah the owner's requirement in terms of DWT or in terms of TEU and whatsoever. Okay, but by then when you develop the hull form, when you develop your basically from hull form you will generate the lines plan, and from that lines plan you will generate your upper GA. Okay, so by then you should have your final main dimension basically. Okay, so that is the main dimension. Maybe it will change a little bit lah. Maybe your L now is 100, so maybe it change 105 or 110, just like that, not changing too much until 200 and so on. Yeah, so there's a little bit tolerance or margin there. Um, okay, based on that GA, you're going to do the stability. And based on that GA, also you're going to do the structure, the scantling drawing and weight estimation later on. Okay, any questions? You have a big CB due to low speed requirement, so later you need to alter the lines plan to match it later. This one is for hull form development, right? We will cover that one next week. There are, of course, the process to alter that lines plan. You mean lines plan of basis ship, right? Yeah, I suppose you mean the lines plan is by lines plan. Okay. Okay, yes. So, okay, so, right, last time once your friend from ASMO finished with the main dimension, I asked them also to find a basis ship. And basis ship, some of your friend, they managed to get a basis ships that almost a similar dimension. Means that if let's say you calculate the main dimension, then you get 100, and then you find a line span that maybe 120, yeah, 120 meter. So it's almost near to 100 meter, right? So, but some of your friend, they did not manage to get a line span with dimension that almost the same as the one that you calculated. Yeah, maybe like Bo, the main dimension maybe 100, but he only managed to find 200 meter punya line span. Okay, because you need to have this line span from any ship, but a similar type ship, yeah, from any previous ships, yeah, similar type of ship, um, to develop the hull form, to develop your own hull form. Okay, otherwise you need to start from scratch, yeah, which is not uh, not relevant. It's not relevant lah. You cannot start from scratch for this ship design. Yeah, otherwise it will take more than 1 year to finish your design. Yeah, so you need to have a basic ship to start with. Okay, if you start from scratch, you should have an experience to do that. You for the time being, we need to have this basic ship. Okay, so back to Go just now. So maybe the case is that Go have a different lines plan, a similar type of shape, but the dimension is way too different. Yeah, the difference is way too big. So then, yes, when you develop the hull form letter, you have to alter, yeah, you have to alter the lines plan to make sure that it match the main dimension that you calculated earlier, based on the GA as well lah. Okay, so based on the initial GA, okay, so you have a new main dimensions. So now uh, this is what we call as the distortion process. I have introduced you a little bit last time, but I'm going to go on detail by next week, yeah, because next week we will start with the hull form. So there are distortion process where you can actually make it bigger or make it make it smaller or make it longer or make it pendek sikit lah, make it shorter, right? There are the distortion um, process that you have go through. So, but you need to have that lines plan first. Okay, you need to have the lines plan. Once you have the lines plan, we will digitize the lines plan to get all the significant points from the lines plan. And from that lines plan, we will do some calculation so that we can alter that lines plan to match our dimension basically. That is our view for next week lah, right? So don't worry, as long as you have a lines plan to start with. Okay. Previously, okay, this is another thing. Previously, uh, 3 members per group, right? 3 members per group, and every member you have a different, basically owner's requirement. Okay, you are given. Okay, this is for the information for SKMO, especially. So last time, let's say general cargo 30,000 ton, 90, yeah. But there are 3 members in the group last time. But every members they have different DWT. Speed is the same, ship type is the same, but DWT is different. Meaning to say that one person will done 30,000 ton. Second member will done, am I correct? 5% higher. So means that 5% higher than 30,000 tons. So should be 35,000 tons. Am I correct? This one? 5% higher. 10%. Is it 10%? Oh, okay, 10%. Sorry, 10%. So 10% higher, which means 33,000 tons. And 10% lower, which means 27,000 tons. Okay. And same goes to the others. So for containers, the 3,500 TEUs, the second member will do 3,000 and another member, am I correct? No. Yeah, 3,000 and 4,000 TEU. Is that 10%? Almost. Okay. Then the same for the rest. But for those who coming from SKMO, so your honest requirement is based on this basic requirement. Yeah. So you will be doing the same as another group members on 3,000, 4,000, 40,000, 30,000, 3,500, 70,000, 40,000, and so on. Okay. Because, okay, last time, different DWT will give you different main dimensions, yeah, but not the difference is not so much lah. Okay, And for hull form development, you also need to develop based on your main dimension. Okay, based on your main dimension. So means that in general